Good morning, everyone. My name's Aman, and I'm the GCSE Chemistry online school tutor. Today's lesson will be looking at the purity of substances, which will include analysing chromatograms and looking at formulations as well, and the gas tests, which we have covered before, but not in so much detail. As usual, if you have any questions as we're going through, please put them into the chat box or the Q&A function. And this session will last for 1 hour, so from 9:45 to 10:45. We're moving on from electrolysis today, and we're starting purity of substances. We have looked at this topic briefly before when we looked at analysing mixtures and separating them, but we're looking at it in more detail today, as it's a separate topic in most of the exam boards. If you haven't met me before, my name's Aman and I study medicine at King's College London, and I've done plenty of lessons with my tutor and all the lessons for the online school GCSE Chemistry. Okay, so the learning objectives for today are to define purity and know how to distinguish between impure and pure substances. We're going to recall how to analyse chromatograms. So as I said, we have looked at this in a bit of detail before, but we're looking at it in a bit more detail today, and we'll be focusing on some exam questions as well. And then we need to know the tests for these 4 gases, and all the exam boards want you to know these tests. All the exam boards want you to know how to analyse chromatograms, and defining purity is mainly on AQA, but they do want you to know most of the exam boards what purity is, and how to distinguish between the impure and pure substances. These are all core topics as well. So before we start today's content, I thought we'd do a quiz testing yesterday's content. So yesterday we looked at the electrolysis of aluminium and brine. So we'll do a quiz on that. So I've got a Menti quiz. So if you go onto menti.com and type in this code, you should be able to join the quiz. So I thought we'd do the quiz at the beginning today to test yesterday's knowledge. Great, so I can see one person's already joined. So menti.com and then type in the code 766910. I'll just wait a couple of minutes for everyone to join. Great, so for those that haven't joined, just go on to menti.com and type in the code 766910. It's free to join. You don't need to make a username or anything like that. I think you can just join. You don't need to make any kind of account. Someone's asking, what do you do on menti.com? It's a quiz. So you'll literally just be typing in answers or selecting the correct answer. So I think I've got 5 or 6 questions based on yesterday's topic. So instead of doing a recap that I usually do, I've done a quiz today. Yeah. So just wait a couple minutes. So we've got 16 of you in it, and I've got about 30 of you in the webinar. So I'll just wait another minute. Anyone that hasn't been able to join by the time I've started the quiz, you can join halfway through, but it will affect how many points you get. So I think we always get a leaderboard at the end, which shows the winner as well. Okay, let's start off then. So I've got 17 of you in it. So the first question should be coming up on the screen now. So what is the ore of aluminium oxide called? What is the ore of aluminium oxide called? Is it cuprite, pyrite, magnetite, or bauxite? We've got about 5 seconds left. Good, most of you got that. Yep, so the ore is called bauxite. Well done. So these are ores of different metals. You don't need to know them. You need to know bauxite, which is the ore of aluminium oxide. So well done, everyone. Okay, the next question should be coming up soon. So what is aluminium oxide dissolved in for electrolysis to occur? So you need to type in the answer here. So what is aluminium oxide dissolved in for electrolysis to occur? So I'll give you a clue. Remember that the electrolysis of aluminium requires a lot of energy, so we dissolve it in something to reduce the amount of energy required to allow it to occur. So 5 seconds left. So the answer was molten cryolite. Yep, so I can see lots of answers there. So cryolite, molten cryolite were the correct answers. So it's not dissolved in water or oxygen. So remember, when we dissolve something, usually it becomes an aqueous solution, but molten cryolite is essentially an aluminium compound. So it stays a molten compound, and that just allows us to heat the aluminium oxide up to a lower temperature in order to get it to melt, basically. That's why we use molten cryolite. So well done for everyone that said molten cryolite. Okay, so the next question should be coming up soon. So why do carbon electrodes need to be replaced frequently during electrolysis of aluminium oxide? So why do the carbon electrodes need to be replaced frequently during the electrolysis of aluminium oxide? Is it because hydrogen breaks the carbon electrodes down? Carbon dioxide burns the electrodes away? Aluminium breaks the carbon electrodes down, or oxygen gas burns the electrodes away? So which one do we think it is? So the answer is that carbon dioxide burns the electrodes away. Excellent, well done. So hydrogen breaks carbon electrodes down. So hydrogen isn't produced when we do the electrolysis of aluminium oxide, because remember, it's a molten electrolysis. That means we get aluminium produced at the cathode and oxygen produced at the anode. But at the anode, that oxygen reacts with the carbon electrodes to produce carbon dioxide, and it's that carbon dioxide that burns the electrodes away. So the answer is carbon dioxide burns the electrodes away. Aluminium doesn't react with carbon, and oxygen gas does react with the electrodes, but it doesn't burn the electrodes away. What burns them away is the carbon dioxide that is produced. So well done. Okay, so the next question is, what is brine? So you'll have to type in an answer to this. What is brine? So it's about what is it made of? What is brine? Got about 10 seconds left. Anyone that's not doing the quiz, you can type the answer in the chat box if you want to. So the answer is sodium chloride, concentrated sodium chloride. Yep, so concentrated sodium chloride. So I allowed NaCl or just sodium chloride. It's not sodium sulfate, it's not a gas, and it's not carbon aluminium. So it's sodium chloride. Yep, so this answer is fine as well. And you could say it's a solution. Well done. So the final question then, what solution is left when electrolysis of brine occurs? So this is about thinking what's produced at the cathode, what's produced at the anode, and therefore what's left in the solution. So brine is concentrated sodium chloride, it's aqueous. So are we left with sodium chloride? Are we left with water? Are we left with sodium hydroxide, or are we left with carbon dioxide? So the answer is sodium hydroxide. Excellent, most of you got that, well done. So sodium chloride is what we start off with. And remember, at the cathode, we produce hydrogen, and that's because sodium is more reactive than hydrogen, so we produce hydrogen at the cathode. At the anode, we produce chlorine. So if we think about what's there, we have our sodium ions, we have our chlorine ions or chloride ions, we have our water, which produces hydrogen ions and hydroxide ions. If the hydrogen ions go to the cathode and the chloride ions go to the anode, what's left is sodium and hydroxide. So that gives us our sodium hydroxide. So they bind together to make sodium hydroxide. So water is a good guess, but remember the hydrogen ions get used up, so it won't be water, and carbon dioxide isn't produced. Only in the electrolysis of aluminium oxide is carbon dioxide produced. Okay, so let's have a look at the leaderboard then. Great, well done to the person that was fastest and also won. I think you won last time as well, so very well done. Okay, I hope you enjoyed the quiz. So let's go on to today's content then. If anyone's got any questions about any of the quiz questions, I'm happy to answer them. But for now, let's go on to today's content. So we're starting off with defining purity. So a pure substance is one that is made up of just one substance. And what that means is that it's made up of either an element or a compound. So when we went through mixtures last time, you'll remember I gave the definitions for element, compound, and mixture. So essentially, a pure substance is not a mixture. It's only made up of an element or a compound, and one of either of them, not both. In the non-chemical world, so basically in the normal world. Pure usually means that it's made up of exactly what it is. So what that means is that if we have orange juice, for example, pure orange juice, it's made up of only freshly squeezed oranges. So when people use pure in the normal world, so when you go shopping or something, they usually mean it's made up of exactly what it says. Whereas in the chemical world, we say a pure substance is something that's made up of either only one element or one compound. And why do we need to know this? Well, it's important to know if when we're analysing a compound or an element that it is pure. And how do we tell if it is pure? Well, we look at the melting and boiling points. And the melting and boiling points basically mean whether that substance is pure. So for example, some substances will have specific temperatures at which they melt and boil. So if we think about water, we know water melts at 0 degrees and it boils at 100 degrees. So if we have impure water or water mixed in with something else, it won't melt at 0 degrees and it won't boil at 100 degrees. Instead, what is more likely to happen is that it will melt at a lower temperature and boil at a higher temperature. So that's the general rule. And the other rule is that it will tend to melt over a wider range of temperatures. So what that means is, for example, if we have our pure water that melts at 0 degrees C, and then we have something mixed in with that water, let's say another compound or something in there that dissolves in that solution, it's more likely to melt at something, let's say -10 degrees, but it will melt over a range. So for example, -10 to -5 degrees. Whereas pure water will melt at exactly one temperature or a specific temperature. So if something is impure, it tends to lower that melting point and it tends to raise its boiling point. So the boiling point of our impure substance might be 110 degrees, for example, and it might boil over 110 to 120 degrees. And they tend to melt or boil over a wide range of temperatures. So how we can tell if something is pure versus impure is about the temperatures that it melts or boils. And the way that we know the temperature that something melts or boils is we use a book or a textbook that gives us all those answers. You wouldn't be expected to learn those. You'd be given them in the exam, and you're more likely to be asked a question like, for example, this substance has this temperature that it melts at. You do an experiment and it melts over these temperatures. Is it pure or impure? So we'll do an example question in just a second to show you that. But all you need to know is that we use the melting and boiling points to tell us if something is pure or not. So someone's asking, what's the difference between mineral water and tap water? That's a good question. So mineral water tends to come directly from the source, whereas tap water tends to come from your local water provider. So for example, mineral water tends to be bottled water that comes from the source. They tend to purify that water, whereas tap water is purified, but it's done by your local water provider. Okay. Let's have a look at these graphs then, which basically show what I was just talking about. So let's imagine the element phosphorus. So phosphorus melts at about 45 degrees. So if we look at the graph on the left, let's say we've got liquid phosphorus, it's then going to melt at 45 degrees. And when it melts at 45 degrees, you can see it happens at a specific temperature over here. So there's a liquid becoming a solid, and we can imagine it the other way as well, so a solid becoming a liquid. So remember, melting and freezing are equivalent to each other. They happen at the same temperature. And this specific temperature is 45 degrees. So that's the graph of pure phosphorus. Now, if we imagine if we have impure phosphorus, what happens is the liquid cools, but as it freezes or as it melts, so if it's going from solid to liquid, it would melt. If it's going from liquid to solid, it freezes. It does so over a wider range of temperatures. And what you can see is that the lower end of that range is actually lower than what the temperature or the melting point is. So the melting point is 45, but if we look on this graph, it goes right down to 40. So the melting point has been lowered and it's over a range of temperatures. So if we had two phosphorus elements, and one melted at 45, which is the temperature that we get told is the temperature for melting the phosphorus, and one melts between 40 and 50 degrees over a range of temperatures, then we know that the impure phosphorus is the one that melts over the range of temperatures. Any questions on that at all? So most pure substances will be made of either one element or one compound. and the person that's asking me about that. Okay, so let's do a typical exam question then. So a student tests the boiling point of a sample of sodium. It starts melting at 185 to 193 degrees, but does not melt completely until the temperature is 205 degrees. According to the data book, the melting point of sodium is 208 degrees. Is this sample of sodium pure or impure? What do we think and why? Just wait for a couple of people to answer that question. So have a read of it again. Good, so pure or impure and why? Good, so it's impure. And the reason, there are lots of reasons. So first of all, it melts over a range of temperatures. So it melts over 185 to 193 degrees. And the point at which it completely melts is lower, 205 degrees, than the point it should melt, which is 208 degrees. So this is an impure substance, and in an exam question, you would answer it with those two reasons. So you would say it's an impure element of sodium, and that's because it melts over a range of temperatures, and it's specific, and it's the point at which it completely melts is lower than the melting point of sodium. This is an exam style question, yes. This is an exam style question. This is just to show you what they might ask you about purity. Okay, any questions about that at all? Does anyone want me to re-go over anything about purity, or are we happy with that? So this would be a 3-mark question, 1 for saying it's impure and 2 for giving the 2 reasons. So it melts over a range of temperatures and its melting point is lower. So remember, when you have an impure substance, the melting point tends to be lower than what the data book says, and the boiling point tends to be higher than what the data book says. And crucially, it melts or boils over a range of temperatures. Okay, great. Let's move on to formulations then. So formulations are still part of the topic of purity. And essentially a formulation is a mixture which has been designed specifically to be used as a product. So it's not a pure substance, but we need to know what formulations are because they are mixtures that are designed specifically to be used as a product. So they are useful mixtures. So usually we're interested in whether an element or a compound is pure, but a formulation is a special type of mixture where we know it's been designed specifically to be made into a useful product. So there's some examples of formulations are paints, medicines, fuels, fertilizers, and cleaning products. So for example, if we think about paints, they're usually put into specific proportions of substances in there, and that's what makes it a formulation. So a formulation will have every chemical added in a specific amount and it's carefully measured, and each chemical has an individual purpose in that formulation. So the key point you need to know for the exams is what a formulation is and why we have them. So the reason we have them is because we need them for paints, medicines. So some examples you can have up your sleeve, and then as well as that, just knowing the definition of a formulation. So it's not a pure substance, but it's a mixture. So it's impure because it's made of lots of different elements and compounds, but it's used specifically for a purpose that we need. So it's not made kind of just by adding lots of different things together. It's done in specific proportions. Any questions about that? So someone's given me other examples of formulations. Yep, that's great. So if you imagine something like a fuel, so we looked at fuels a couple of weeks ago, or last week actually, and we saw that you actually have to break fuels down to make them into single elements or compounds and by cracking. But when we think about fuels in general, they're made of lots of different alkenes and alkanes, and that's why they're not pure, but they're put into a specific proportion to be used. Yep, if you've got a question relating to this topic, you can type it into the chat. That's absolutely fine. Someone's asking me, for chemistry, physics, science, triple science, how many marks would each paper be for AQA? I'm not entirely sure about that. It used to be 60 marks for each paper, but I think that's changed. So if anyone knows the question, answer to that, with the AQA papers, how many marks are each of the papers? 80. Okay, so it's gone up to 80. So 80 marks per paper. Okay, someone's saying 100, and some people are saying 80. Okay, I'm not entirely sure because it used to be 60. The old papers were 60, but it's gone up. So it's either 80 or 100 there. what I'd recommend is having a look at an old past paper. Okay, let's move on from formulations then to chromatography. And as I said, we have looked at this before, but I want to look at it in a bit more detail today to make sure that everyone understands it, because all of the exam boards want you to be able to have a clear grasp on paper chromatography and specifically to be able to analyse chromatograms. It's a very common exam question. So why do we do paper chromatography? You may remember from when we looked at it last time that it's used to separate mixtures of soluble substances. So things that are made of soluble substances. So if we think about something like a paint, usually that's made of different soluble chemicals, and we would do paper chromatography to separate out all those different colours or all those different chemicals. Someone's saying, isn't chromatography a year 7 to 8 topic? No, it gets a lot more tricky. We'll be looking at that today, kind of what we need to know for it. So you might learn about it in year 7 or 8, but at GCSE you build on that knowledge. So the mobile phase is the solvent that carries, or the solvent that moves through the paper, carrying the different soluble substances with it. So for example, in this picture over here, the solvent is the water. So the mobile phase will be the water carrying those different chemicals through the paper. The stationary phase is the paper itself. So we've got the mobile phase, which is what's moving. So essentially the dye is moving with the water up the paper. And the stationary phase is what stays still, so the paper will stay still. And it's important we know what the mobile and stationary phase is. And the reason for that is because when we get into kind of the GCSE questions, we need to be able to describe why something moves higher up versus lower down. And the reason for that is to do with attraction. So what this says here is that the different dissolved substances in a mixture are attracted to the two phases in different proportions. And that causes them to move at different rates through the paper. So what that is saying is that depending on their attraction to the mobile versus the stationary phase, so remember the mobile phase is the solvent that moves through the paper, so in this case the water here that's moving through the paper to carry those inks up, and the stationary phase is the paper, usually filter paper. And so it's about the attraction to the filter paper versus the solvent. So if a substance is more strongly attracted to the mobile phase, it will move further up the paper. So if we take this one here, we can see that's moved quite far versus this one here that's moved less far up the paper. And the reason that this red blot here has moved so far up is because it's more strongly attracted to the mobile phase or to the solvent, and that then allows the solvent to carry it further up the paper. Whereas this blue dot down here, it doesn't move so far up, and that's because it's less attracted to the mobile phase and more attracted to the stationary phase or the paper. And so that means it moves less far up the paper. So it's important that we understand why certain substances move further up or less far up depending on their attractions. So someone's just sent me an exam question. I will have a look at that in just a second once I finish going through chromatography. Okay. So any questions about attractions then? So it's about how far an ink or one of the chemicals in the chromatography paper moves up. If it moves further up, it's more attracted to the mobile phase and less attracted to the stationary phase. If it moves less far up, it's more attracted to the stationary phase and less attracted to the mobile phase. Okay, so no one sent me any questions on that, so I'll assume everyone's happy with that. So let's just have a look at this paper or this chromatography chromatogram here then. So we've got a mixture and we've got 3 dyes. So what is this mixture made of then? So in an exam question, they might ask you what your interpretation is of this chromatogram. And I'm sorry, it's so small. Let me see if I can make it a bit bigger. Oh. So this is a mixture. What is the mixture made of, or what can we say about that chromatogram? Good, it's made of dye 1 and dye 3. And the reason we know that is if we have a look at the mixture, we've got a blue dot here and a blue dot here. So that means the mixture is made of dye 1 and dye 3, because we've got a red dot and a red dot. But the yellow dot isn't in that mixture. So often we do chromatography to figure out what is in a certain mixture of dissolved substances, and that's how we analyse a chromatogram. Excellent, well done everyone that answered that question. Someone's asking, what's the mobile phase? So the mobile phase is the solvent. Sorry, let me just put that back at 100. Yep, so the mobile phase is the solvent that moves through the paper, carrying the different soluble substances with it. So essentially in this case, it's the water that the filter paper is submerged in, but it's not submerged too far up. So does anyone remember what we need to know about chromatography and how we do it? So there are a couple of points when we do chromatography that are really important, and exam questions love to ask you about kind of setting up the chromatography equipment. So what's really important? Someone's asking how and why do the dyes overtake the other colours? So they're not necessarily overtaking. Again, it's about their attraction. So for example, when we put this mixture on this blot, the mixture will separate into its different dyes. And then if we want to know, well, actually, what are those different dyes? We need to guess and put some other dyes on the chromatography paper. So we've assumed that the mixture might be made of 2 dyes, or sorry, 3 dyes. We don't know which of the 3 it could be made of though. So we put blots of these 3 dyes and we do the chromatography. And when we do the chromatography, the 3 dyes will split into their colours and the mixture will split into its colours. Remember, the dyes are pure substances, so they're only made of one element or one compound here. So we can see that these dyes are pure, but the mixture isn't. It's made of 2 different elements or compounds. And so what that means is that when we do the chromatography, they move up the paper, and it's about their attraction to the mobile versus the stationary phase as to how far they move up that paper. So this red blot is more attracted to the mobile phase than the stationary phase, so it moves further up, whereas this blue dot, which moves less far, is more attracted to the stationary phase than the mobile phase, so doesn't move so far up the paper. Okay, so great. So loads of people have given me things that we need to know about chromatography. So the first thing is the start line needs to be done in pencil. Great. Do not draw it in ink. Only part of the paper should be submerged under the water. Excellent. Use a special solvent, not just water. Yep, that's also important. And evenly space the dyes. Good. Well done. So I'll type that out. So we need to draw the start line in pencil. So start line in pencil. So that's one of the main things. And the reason we don't draw it in ink is because the ink will allow the dyes to run, or the ink can also run as well. So if that solvent reaches the ink will run. That basically defeats the object of what we're doing. We only want the dyes to run. We don't want the ink to run. We need to evenly space our dyes, or whatever we're doing chromatography on. As well as that, you need to make sure that the solvent does not reach the baseline or the start line. So it's really important that the solvent does not reach that start line, because otherwise it will essentially dissolve the dyes, and we don't want that. We want the solvent to move up itself up the paper. Good. Okay, so they're the 3 kind of main points. Someone said that you can change the solvent. Yes, you can. At school, you tend to use water. You won't tend to use anything apart from that, and the paper will be filter paper. Great. Okay. I think we had a question about RF values. We're going to go on to RF values now. And someone was also asking me about gas chromatography. No, it's not on the GCSE syllabus. So when we looked at separating mixtures, it's not on the GCSE syllabus, so we're not looking at gas chromatography. Are the different compounds and elements the different colours? Yes, they are. Well done. Yes. Okay, so paper chromatography. So a pure substance will have only 1 spot on the chromatogram, which is what I talked about. So if we go back to these, we can see these 3 dyes are all pure. They've only got 1 spot on the chromatogram. An impure substance will have more than 1. So if we have a look, we've put a spotted sample of a reaction mixture and it's got 3 dots on it. These 3 dots mean that this substance is impure because it's not made of 1 dot, it's made of 3 dots. And the final thing that we need to know about chromatography is we need to be able to calculate the retention factor. And essentially the retention factor is a calculation where we look at the distance the spot travels up the paper. So the distance the dot travels up the paper, so distance dot travels up the paper divided by the solvent front. And the solvent front is essentially where the water which is our solvent, stops once it's traveled up. So it will travel up the paper and at a certain point it will stop. And where it stops, you will get this line, and that is called the solvent front. So it's basically the distance the solvent front travels. Distance solvent travels. I'll just put the solvent at this point, but it's called the solvent front if you want the proper name for it. Okay, what's the difference between RF, MR, and AR? Good question. So MR and AR relate to the relative atomic mass and the relative formulae masses of elements and compounds. RF is only chromatography. It's nothing to do with the MR or the AR. Do we have to draw the solvent front? No, in exam questions, they will usually draw it for you. When you're doing it at school, you'll see clearly where the water stops traveling. So you can either just measure up to that or you can draw a pencil line if that helps you to measure it. Okay, so that's the calculation. So distance the dot travels up the paper divided by the distance the solvent travels. So if we have a look at this question here, so we can see that the distance the solvent travels is 5 centimeters, and the distance that each of these blot travels are 1, 2, and 3 respectively. Can the solvent be in powder form? No, not for paper chromatography. It needs to be a liquid of some sort because otherwise the dyes will not separate. Okay, so the retention factor of C then. What's the retention factor of C? So it travels 1 and the solvent front is 5. So what's the retention factor? You can give me the answer as a fraction or a decimal or a percentage, whatever you prefer. Good. So we've got lots of different answers. So 0.2 or a fifth. Excellent, well done, good. What about A? What about A? So if you can't see the numbers, this says 5, this says 3, 2, and 1. Good, A is 0.4, so 0.4, so it's 2 divided by 5, which is 0.4, or you can say 40%. And then finally B, what's B? Good, yep, 3 out of 5 or 60%. So in exam questions, they might give you the numbers or they might ask you to work them out. And what's really important then is that you use the ruler. Okay, so I've got a question for all of you about how you measure the chromatography. So where do you measure to? Do you measure to the middle of the blot or do you measure to the top? Where do you measure? Where does the 5 come from? The 5 is the solvent front. So remember I said that the equation is the distance the spot travels up the paper divided by the distance the solvent front travels. So the distance the solvent front travels is from the origin right up to where the solvent front is, and they've said that that's 5. And then the distance of each of these blots are 1, 2, and 3 respectively. So that's where the 5 comes from. Good question. Okay, good. So we've got lots of different answers, and I'm glad we've got lots of different answers because it's actually quite confusing. So from all the teaching that I've done, I always say the middle of the blot. And in the AQA, EdXL, and OCR textbook, they don't actually say, but from talking to other teachers and things, it is the middle of the blot. That's where I will always measure to, and the exam questions will be fine if you measure to the middle. And the reason that I believe we do that is because when we put a blot on our origin line, we will blot it like that, and the origin line will go through the center of that blot. You don't put the blot on top of the line, you don't put the blot below the line, you put it on the line. So essentially we go from the middle of the origin, so from the middle of the line or the middle of the blot to the middle of the blot. So we always measure to the center. So yeah, so the people that said the middle, you're correct. So remember, you always measure with your ruler to the center. So middle to middle, that's how I remember it, and that is what makes sense as well to me. And good, well done everyone. Any questions on that before we move on? So there are no units for RF, it's just an equation that we do, there's no units for it. It's like the atomic mass and the relative formula mass, they don't have any units, they're just a specific measure. So no units. Good. Okay, so an exam question. So a mixture of amino acids was tested against 5 known amino acids, 1 to 5, and the following chromatogram was made. What can we say about mixture M? So I'm looking for a couple of points here. So it's a 3-mark question. So I'm looking for 3 points. Okay, let's see what people are saying. Good, so it consists of, I wouldn't say 4 dyes because we're looking at amino acids. So this is not to do with dyes. but good. So it consists of 4 different, the mixture has 4 amino acids in it. So what's really important is that we read the question carefully, because if we have a look, this is saying there's a mixture of amino acids and they were tested against 5 known amino acids. So essentially when we're answering this question, a lot of the marks come from being very specific about saying that actually mixture M is made of 4 amino acids, and they are 4, 5, and 1, but we don't know what this one is. So we can say mixture M. Actually, let me type this out. So mixture M is made of 4 amino acids, first of all, and that's because it has 4 blocks. And what we can see is amino acids 1, 4, and 5 are present within mixture M. And then you can say one of the amino acids cannot be identified. Okay, so that would give you your 3 marks. So what about if I asked you about the attraction? What can we say about the attraction of this blot compared to this blot? So blot 1, or amino acid 1 compared to amino acid 5. So what can we say about the attraction between amino acid 1 and amino acid 5? I wouldn't say elements or compounds, because amino acids are not elements or compounds. So in this question, it's really important that you read the question, because it tells you that you've got a mixture of amino acids and they were tested against 5 known amino acids. So you know each of these are amino acids, and the 5 amino acids are pure because there's only 1 blot on the paper, whereas the mixture is impure because it's made of more than 1 amino acid. So an amino acid is a compound. Okay, good. So we've got a few answers to the attraction. So someone is saying number 1, amino acid 1 is more attracted to the mobile phase, and number 5 is more attracted to the stationary phase. Excellent. Yes, that's exactly correct. So the answer to the attraction question then is amino acid 1 is more attracted to the mobile phase, and so moves further up the filter paper, whereas amino acid 5 is less attracted to the mobile phase and more attracted to the stationary phase. Therefore, it moves less far up the paper. So that's quite a long answer, but hopefully that makes sense. There you go. Any questions on that? How do you tell if it's attracted to the mobile or stationary phase? It's a really good question. They will both be attracted, or sorry, all the amino acids will be attracted to both of those phases, but it's about whether it's more attracted to one phase versus more attracted to the other. So if it moves further up the paper, it's more attracted to the mobile phase, which is the solvent essentially, and that means it moves with the solvent. And remember, the solvent is mobile. So if it moves further up, that means it's more attracted to that solvent, more attracted to the mobile phase. Whereas if it moves less far up, that means it's a little bit more stationary. It's more attracted to the paper than the solvent. So we say it's more attracted to the stationary phase. Someone's asking, can we talk about the impurity of the substance for the 3-mark question? Yes, so you can say that mixture M is impure, but make sure when you say it's impure, you say it's made of 4 amino acids, and that's what makes it impure. Whereas the 5 amino acids are pure because they're made of only 1 amino acid or 1 compound. Good questions. Okay, right, let's move on to the next topic then. So the 3 marks were just in this light blue, so this is the 3 marks here. This is just another question that I had about attraction that you can also be asked about. Someone is sending me Wikipedia things that I'm not sure why you're sending me. So, okay, fine. Let's go on to the tests for gases then. So the final part that we're going to learn about today are the tests for gases. I am not going to fill this table in. I'm going to get you guys to do it for me because I know we've been through the tests for all of these gases before, but I just want to make sure that everyone's on the same page and understands them, and then we'll watch a quick YouTube video for all of those tests. So what is the test for hydrogen? Yeah, the squeaky pop test. Yeah, I like that, the squeaky pop test. So essentially, you have a lighted splint, so it needs to be lighted, and you put it into a test tube of hydrogen, it will make a squeaky pop sound. So a lighted splint will go pop in a test tube of hydrogen. So that is the test for hydrogen. So a lighted splint will go pop in a test tube of hydrogen. Good. Okay, what about oxygen? So I've got a few answers. Yeah, it relights a splint. And so what's really important about it relighting a splint is that usually you have a splint that is glowing and you blow it out, but you will still see embers. And what I mean by embers is it will still kind of be a bit red. So it will relight a blown out splint, or you can just say it will relight a splint. Some people allow relight a glowing splint. But yeah, relight a splint. Good. What about carbon dioxide? Good. Yep, lots of answers about turning lime water milky. Excellent. Lime water. You can say cloudy. I think examiners don't mind between cloudy or milky. But essentially, you've got to bubble the CO2. So bubble the carbon dioxide, CO2, through lime water. And that's really important. If an exam question has 2 marks, the reason it has 2 marks is because it wants you to say that you will bubble the carbon dioxide through the lime water, and it will turn cloudy or milky, whichever you prefer. We'll watch a video in a second, so hopefully you can see that. Okay, so the final one then is chlorine. What's the test for chlorine? Yes, so it bleaches litmus paper. So by bleach, that means it turns white. Good, yeah, so usually it's damp litmus paper. So damp litmus paper will bleach, and that just means it turns white. Excellent, well done everyone. So hopefully for anyone that was unsure about the gas tests, you are now sure of those. We'll watch a YouTube video and then we'll do some exam questions on everything we've covered today.
Welcome to this episode.
Okay, so we're testing gases. Okay, so this is the oxygen test. So he'll do it again in just a second. So he's blowing it out there. So you can see it's blown out. He's going to put it into the oxygen and there you go. You can see it's been relit. Okay, so that's the test for oxygen. So you blow out your splint. You'll still have red embers there. You can see it one more time. So you can see the red embers, but it's blown out. And then you put it inside a beaker of oxygen and it will relight. Okay, great. So this is the test for hydrogen gas. This is a bit difficult now because I can't get you to hear the pop. But essentially when you put, so he's just going to make some hydrogen first of all. So he's reacting hydrochloric acid with a metal to make hydrogen. And he's made some hydrogen there. You can see that because of the effervescence. And then when he puts a glowing splint, so now you can see it makes a pop sound. I don't think you guys can hear it. So what I'm going to do is I'm going to leave the link. It's on the chat anyway, but I'll send it to you all in the chat box in a second so you can listen to that in your own time. But you'll be able to hear a squeaky pop when he adds the glowing splint to the test tube of hydrogen. Someone's asking me what's effervescence. Effervescence is a fancy word for bubbling. And usually if you see effervescence, there is a gas produced, most commonly hydrogen. Okay, let's go to carbon dioxide. So there's our lime water. So he's poured some lime water in there and he's going to bubble the carbon dioxide through that lime water. So he's just going to make some carbon dioxide first. Yep, this is a core topic, so you would need to know this for foundation. So there are calcium carbonate chips, which will help us to make carbon dioxide. When you add calcium carbonate to the acid, we get carbon dioxide. So he's produced carbon dioxide. He's now going to use the bung and the tube so that we can bubble that carbon dioxide through the lime water. So we can see carbon dioxide is being produced. He's going to bubble it now through the lime water. You can see the bubbling going on here. And what's going to happen is that lime water was clear and it's now going cloudy or milky. So you can see that happening there. So that's the test for carbon dioxide. Okay, so you can see that's clearly gone quite milky or cloudy. Okay, and then the last one we'll look at is for chlorine. So first of all, he's just going to make some chlorine and then he will use litmus paper and it will bleach. So he's just making some chlorine gas. So we can see some gases being produced because we can see the effervescence there. So remember, effervescence just means bubbling and it usually means a gas is being produced, and that's our chlorine gas. And now if he adds the litmus paper, there it is, that's the damp litmus paper. He will add it to the gas. So you don't need to add it to the solution, just kind of above where the gas is being produced. What you'll see in just a second is that the litmus paper, there you go, is bleaching, is going white. And that's what happens with chlorine. Okay. It doesn't have to be a blue litmus paper. I think the usual exam questions, you just need to say damp litmus paper. You can say blue or red. Usually it is blue that we use, or purple, so blue litmus paper that is damp. Okay, let me just send the link into the chat so all of you can see that. Oh, not there. There you go. So I've just sent it to all of you so you can see that. If you have a look at that link, you can have a look in your own time and you can see, listen to the hydrogen test. Would the litmus paper stay bleached? Yes, it would. The bubbling word is effervescence. Effervescence. Right, hold on, effervescence. There you go, effervescence. It should be in the chat box. If you haven't got it, it should be in the chat function. Okay, you can't see it. That's interesting. Oh, let me do it again. Hold on. There you go. You should be able to see it now. Okay, great. So it's in the chat box now. That's the link to the YouTube video we just watched, and I would recommend watching that in your own time. Okay, so just as a quick recap of what we've covered today then, so we looked at purity and we know how to distinguish between impure and pure substances. So it's about the melting and boiling points. We recall how to analyze chromatograms. So we looked at the attractions to the stationary and mobile phase, and we looked at calculating the retention factor. And we looked at the tests for all of the 4 gases, and we watched a video as well to hopefully make that make sense. Someone's still saying they haven't got the link. Okay, let me. Okay, hold on. It should be in the chat box. I've tried to send it to some of you if you haven't got it. Okay, have you all got it now? Great, okay. So let's do an exam question then. So this question is about mixtures and analysis. Which 2 substances are mixtures? Air, carbon dioxide, graphite, sodium chloride, or steel? Which 2 mixtures which 2 substances, sorry, are mixtures? Okay. So sodium chloride is not a mixture. That is an ionic compound. Graphite is not a mixture. It's made of carbon. Carbon dioxide is a compound. It's made of carbon and oxygen. It's a covalent molecule. Good. It's air. Excellent. And steel. So steel is an alloy. So air and steel. Good. Well done. So air and steel. Okay. So what is the definition of pure substance in chemistry versus pure substance in everyday life? So I definitely covered this in one of our first slides. So a pure substance in chemistry versus a pure substance in everyday life. What do we think? If I label this 1, 2, 3, 4, and 5, I think number 5 has been cut off. Let me show you. Number 5 just says substances at the end. So a useful product made by mixing substances. That's how that sentence ends. What do we think? Pure versus impure? Okay, so people are saying pure is number 2. Good, a single element or single compound. What about pure in life then? So pure in chemistry is number 2. Excellent. What about pure substance in everyday life? Good, everyday life, it has nothing added to it, number 1. Excellent, well done everyone. So remember, the example I gave was orange juice. So if something says it's pure orange juice, that means it's concentrated and therefore it only contains pure squeezed oranges or just oranges in it. So it's only got oranges in it, whereas in chemistry, it's a single element or a single compound. Excellent. What is the test for chlorine gas? So we've just seen this. And notice how they've not given the color of the litmus paper. As I said, you don't need to give a color. Good, yep, number 3. So damp litmus paper turns white. So a glowing splint relights is a test for oxygen. So this is why often they like you to say glowing, because the difference between hydrogen and oxygen is that the hydrogen test will be a lighted splint, whereas when you've just got embers at the end of a splint, we call it glowing. So if you differentiate between the hydrogen and oxygen by saying that hydrogen is a lighted splint, whereas oxygen is a glowing splint, damp litmus paper turns white is chlorine, and lime water turns milky is CO2. Good. Okay, this question we haven't covered today. We will be looking at it next week, but if anyone wants to have a go, they can do. Does anyone know which metal is in the metal chloride solution? So which one is brown? Does anyone remember? So it's iron 3. It's not copper, it's iron 3. It's iron 3. And we'll go into details of the ionic the ions next week. So I'm not going to explain that today. We'll go into the detail of ions next week. Excellent, well done for everyone that said iron. Okay, so chromatography then. Give a reason why the start line is drawn in pencil rather than in ink. So a compound is usually 2 elements chemically combined. 2 or more elements chemically combined. Good, yes. So if you draw the start line in ink, the ink will either dissolve in the water or it will run. Good, yep, any of these will be fine. The pencil line does not dissolve in water, it will not run. Good, pencil is insoluble. Any of those is absolutely fine. Good. Okay, the chromatography paper with the spot of mixture on it was placed in a beaker at the bottom of the water. On figure 2, complete the diagram showing the position of the chromatography paper with the spot of the mixture at the start of the experiment. So this is one of the only questions I've ever seen where they've asked you to actually draw the equipment. So let's have a go then. So if you tell me what do I need to draw, where do I need to draw it? So they want to complete the diagram with the position of the chromatography paper. So that means I need to draw the chromatography paper and a spot of mixture. Good. So first of all, we need to draw the chromatography paper. So the chromatography paper can look a bit like that. And what's really important when I draw this chromatography paper? What's important? Should it be going all the way down? Should it be going to here? Where should it go? Good, it must be in the water, but only slightly. And then what's really important is that your pencil line that you draw is above. So the pencil line is not this water line, that's just the water line. So I need to draw a pencil line, which we can draw like that, like so, and you label it. So when we are labeling this, we need to say this is our chromatography paper or our filter paper. So chromatography paper, filter paper, whichever you prefer to say. We need to say that this here is the pencil line. And what's vital is that that pencil line is above the solvent line. And then we need to draw our spot of ink. That's the only thing missing. So if we draw our spot of ink, like so, try and make sure it's a rounded blot with the center in the pencil line. Good. Well done, everyone that gave me answers to that and tried to answer it. Okay, so I think some of you have tried to answer this RF. So good, so I'll just let anyone have a go at that hasn't already. So it says the blue spot has moved 14.5 centimeters and the solvent front has moved 15.3. Calculate the RF value of the substance in the blue spot. Yep, so 14.5 divided by 15.3. Good, well done. 14.5 divided by 15.3. I think it's better to give it as a decimal, so 0.95 would be the answer. There's no units, so 0.95. Excellent, well done. Good job. Okay, let's go on to the next question. Okay, PQ, R and S are mixtures of food colorings. They're investigated using paper chromatography. Figure 4 shows the chromatogram at the end of the experiment. Which mixture contains an insoluble food coloring? Which mixture contains an insoluble food coloring? Good, yep. Everyone's sending me the right answers so far. It's not R, it's not R, it's Q. And the reason it's Q is if you have a look at the line, Q's still got something on the start line. So what that means is that the solvent hasn't been able to dissolve part of whatever's in Q. So it's got an insoluble food coloring, and therefore Q you need to do something about that, because not all of the substances in Q are soluble. Good, okay. By the way, are PQ, R and S pure or impure? Okay. Excellent. So P, Q, and S are impure, but one of them is pure, and that's R. That's because R only has one blot. And so that means that its food coloring is only made of one element or one compound, whereas P, Q, and S are made of multiple. Good. Well done. Okay. What can we do to make the experiment, to obtain an RF value for the insoluble coloring? So what can we do? Yep. So someone's giving me the correct answer. Good. Yep. Good. Use a different solvent. Excellent. Yep. Well done. So the person that said change the solvent, you're exactly correct. Well done. So use a different solvent. And if we use a different solvent, hopefully that will dissolve Q. So excellent answer. Well done. Okay. Explain by referring to figure 4 which mixture is separated into the greatest number of soluble food colorings. So which mixture has the greatest number of soluble food colorings? Excellent. S. Why? So it's 2 marks, so you need to say S and a reason. So you won't just get both marks for saying S. Because it has 4. Yes, good, well done. So what you can see there is it has 4. And there are your 4 blots. Whereas the others, so P has 3, Q has 3 plus an insoluble substance. So we can't say that Q is the mixture that's separated into the number of soluble food colorings. And the reason that they don't want you to say Q is because of these words here, by this chromatography experiment. So what that means is we don't actually know about Q. So that's why we can only say, based on this chromatography experiment, that it's S, and R only has 1. So yes, it's S. Well done. Good. Okay, so we will do this as our last question and we'll finish up. So chromatography was carried out on a sample of soft drinks to check that they contained only colours that were safe. This is the result. What conclusions about the safety of the colours in the soft drinks A, B, C, and D can be made from the results shown by chromatography? What can we say? Yeah, so someone is saying they're all safe. They're not. So it's a bit difficult, this question. Let me see if I can zoom in a bit. Oh. So this is basically our mixture, and we are trying to work out what it contains. And what we can see is that B and C are the safe colours. That's why the safe colours underneath B and C, whereas A and D are not. So if we have a look, this mixture contains B, which is a safe colour, C, which is a safe colour. It contains something in A and B, but that's okay because it's in B, so it must be a safe colour. And then it contains this one here. And this one here is in C and D. So what can we say then? Is it safe or is it unsafe? Good, so it's about saying that it is safe. And what do we need to know then? Someone's saying we're meant to, I'm not sure what someone's saying actually. Good. So A and D are not safe, but B and C are safe. So that will give you 1 mark. And then just for saying that the colours in the mixture are shown here. Okay, so I see what someone's saying. So I think the reason this question is a bit confusing is because the safe colours is supposed to be under this chromatography gram, and the colours from the soft drinks are over here. Fine. Okay, so let's rearrange that question and do it again. So this should be here. So these are the safe colours. And this should be here. So sorry, the question has messed up slightly. So let's have another go. So if these are the safe colours, which of these then are safe? So it's still pretty much the same anyway. So B is safe because it contains this one, and C is safe because it contains this one and this one, but D contains this and this, which we don't know about. It's not on the safe spectrum, and A contains this and this because it's not on the safe spectrum. So yeah, everyone that said A and D are unsafe anyway, we had the right ones there. Okay, good. So well done everyone today. I hope you enjoyed the lesson. I will see you next week, where we'll be looking at the tests for positive and negative ions and more on this topic. Have a lovely weekend. And as I said, I'll see you next Monday, I think. All right, take care everyone. Bye.